Okay, so welcome again. My name is Wolfgang Wagner from the Vienna University of Technology. Maybe could somebody of you confirm that you hear me well and that you see the slides? Okay, thank you very much. Great. So we're a small group of people, so please don't hesitate to ask any questions during the talk. You can put something into the chat, or you can unmute yourself, I guess, and ask questions. So please don't hesitate. So I'll talk about soil moisture products at continental scale. This is a webinar series from the EO for Africa project, with which you're familiar with. So just to give an overview of all the different webinars that have been taking place already. So you see most of the webinars have already been held, and some of the webinars before also were held by our team at TU Wien. So we already talked about flood mapping with Sentinel-1 data. We talked about global flood monitoring and surface soil moisture anomaly mapping and drought monitoring case studies in Africa, which was the last webinar. So we basically were dealing in those talks with high resolution flood data and more coarse resolution soil moisture data. And today the focus is more like on higher resolution soil moisture products that at the moment are typically available at continental scale, but they are also becoming now more and more available at a global scale. So just again on the background, why this talk focuses on the use of microwaves for soil moisture remote sensing is this is because with microwaves we are in a good situation that we can obtain measurements all year round under all weather conditions, and microwaves have a capability to penetrate deeper into vegetation and soil. So the longer the wavelengths is, typically the more beneficial it is for the estimation of soil moisture. So this is why if you look at the frequency range, and if you look at the different frequencies where popular soil moisture sensors are working, those specifically designed for soil moisture monitoring are the SMOS satellite and the SMAP satellite that work at L-band at around 1 gigahertz, and operational sensors like ASCAT and Sentinel-1. They're also like below this 10 gigahertz threshold where the dielectric properties of waters, drop off drastically. So also here, we're still very sensitive to changes in the soil moisture content. Here in the L-band, you're a bit better, as you see here, more in this strong response of the dielectric constant. So the reason why microwaves are particularly sensitive to the water content is because water molecules have a permanent dipole moment where the charges are separated between the oxygen and the hydrogen. So if there is now an applied external electromagnetic field, those water molecules start wobbling and basically react to the applied field by re-emitting radiation, which is then being seen by the radar, respectively by passive microwave sensing techniques. Here's an overview of popular sensors and giving you a bit kind of, this C-band, L-band sensors. So on top you have the SMOS sensor that was launched in 2009, which was the first sensor dedicated for the retrieval of soil moisture. In 2000, well, I forgot the year when it was launched, but sometime later came the SMAP sensor that is now delivering since many years already very good soil moisture products. And upcoming will be the so-called NISA mission, a joint mission by NASA and the Indian Space Agency, which will deploy kind of a very large synthetic aperture radar antenna to make fine resolution measurements of L-band backscatter, and it will also be serving different soil moisture estimates. Below you have C-band sensors like the Japanese passive radiometer here and the advanced spectrometer from EUMETSAT here, and then the high resolution Sentinel-1 C-band backscatter data that helps us now to get to a much finer scale in terms of soil moisture. So Sentinel-1 will be the focus of this talk. So from the previous webinars and different training modules from this EO Africa, you've heard that there's already several coarse resolution soil moisture products which are operationally available, like from SMAP, from SMOS, from ASCAT, from EMSA2, and a combination of all of them. And what's now really important, but for many applications, is that we move to a higher spatial resolution. So that we move to a resolution that goes in the order, say, from about 100 meters to 1 kilometer. Obviously, going to this much higher spatial resolution is much more challenging, both in terms of the sensor characteristics, so that we have those measurements on a frequent basis. And it's also much more challenging in terms of the retrieval algorithms, because the finer the spatial scale is you're looking at, the more processes you basically need to consider in the retrieval process. But of course, it's a very important requirement. And there was, like in 2001, a paper by Peng et al. That laid down a roadmap for high-resolution satellite soil moisture applications. And they highlighted those applications that would particularly benefit from a higher spatial resolution, like, for example, hydrology or agriculture or forestry, that would benefit significantly if you can give them data at this spatial scale. Other applications like numerical weather prediction or climate, they can live at the more coarser scale. But even if you look, for example, at numerical weather prediction, the latest generation of models is moving to the 10-kilometer scale. They are now having developments to move to the 1-kilometer scale. So even for weather forecasting and climate prediction, the 1-kilometer scale starts to be highly relevant. And how is it achieved? How do people go to this higher resolution? So I would say there's two approaches. The one approach is that you try to downscale the coarse resolution microwave measurements to the finer scale, or the other approach is that you directly retrieve soil moisture at the finer spatial scale. I would say more prominent right now in terms of the availability of products is the first approach, so that you downscale SMAP, SMOS, ASCAT, EMSA2 data. And there's different approaches. The one would be that people start from level 1 satellite data products, for example, brightness temperature measurements from SMAP and SMOS, or backscatter coefficient from ASCAT. And the other approach would be that you start from level 2 data, so that you start from like SMOS and SMAP soil moisture estimates. And then there are two principal sources of how data then downscale is either using optical data, like, for example, from MODIS or Sentinel-2, or from synthetic aperture radar data, like Sentinel-1 in particular. So here you see a publication by a colleague from Spain. This approach, she published the approach already in 2011, but since then there is like a series of papers that have improved on the product. But basically, this figure shows nicely the idea, what is being done, that you use coarse resolution microwave measurements, like in this case from SMOS brightness temperature at 40-kilometer grid. And then you combine it somehow with optical data at 1-kilometer scale. So here is like the surface temperature product, and here would be a vegetation data product. And then you use some kind of algorithm to merge the three products. So here would be a very simple procedure by building like a regression model or a machine learning technique where you throw in the different input data sets, and out comes a soil moisture estimate. So you would try to have, like, the anchor of your retrieval would be the coarse resolution microwave data, and the finer resolution data would then be kind of to disaggregate the information to a much finer spatial scale. So it would go here from the 40-kilometer surface soil moisture estimates from SMOS alone to the soil moisture estimates here 3 kilometer, at 10 kilometer, and here to 1 kilometer, each one adding more spatial details. I think the important point to make is, unfortunately, it's still very difficult to validate soil moisture data at such fine spatial scales. So you may get the impression, well, these images look much better, and you might think immediately, oh, this could be much more useful for my application. But the point is, unfortunately, at this moment, we still have very limited information and capabilities to actually validate data at this very fine spatial scale. So that in many cases, when there are studies trying to use different soil moisture product, people find very little benefits of using the higher resolution data compared to the coarser resolution data. Of course, there's more and more studies that show the positive impact, of the high resolution, but still it's work in progress. I think that's overall the status that you need to be aware with, that the progress or the operational readiness is much better with the coarser resolution soil moisture data than now with the higher resolution products, as I've discussed today. Possibly the most widest used higher resolution product would be the one that combines the SMAP and the Sentinel-1 data. This is done in such a way that the brightness temperature data from SMAP are somehow combined with the backscatter data from Sentinel-1, so that you downscale the brightness temperature from say the 9 kilometer to a 3 kilometer grid, and then to a 1 kilometer grid. And from there, you do the retrieval with the normal kind of forward models to go to soil moisture at 9 kilometer, 3 kilometer, and 1 kilometer scale. So you see how you add spatial detail from here to here to here, and basically this would be the native SMAP data here, and here you would bring in successively the information from the Sentinel-1 data in terms of the spatial detail. So the question, how can it be done that you combine brightness temperature with backscatter data to kind of get a high resolution brightness temperature map out of it? Well, the answer to this question is that because brightness temperature and backscatter data are highly correlated, because both are sensitive to soil moisture. So they are not independent measurements. So this is why you can use backscatter data to downscale the brightness temperature data. So that you then would, what the SMAP team is doing, they're building a relationship between backscatter data at the pixel scale and backscatter data at the coarse scale. So C stands for the coarse scale, with the brightness temperature data at the coarse scale and the target grid. And by establishing this relationship, they downscale the brightness temperature data. And what the overall assumption between is that there's a linear relationship between brightness temperature and backscatter at the appropriate scale. What's also behind this is, and why this works for soil moisture in this ways, that's already something I brought in previous, not the webinar, but in different training sessions, that soil moisture has the property that it scales across spatial scale according to a phenomena called temporal stability. So what does temporal stability mean? So consider that you have like an in situ measurement networks with stations that are hydrologically independent, but they are within the same kind of climate context. Yeah, imagine that you have a network that's within an area of 10 by 10 square kilometer, and then you have individual stations at many individual agricultural fields, like for example here in the Remedios network in Spain. And then you can take measurements from each individual station, or think about a pixel from the satellite measurements, and then you have one time series. And you take then, of course, many time series from the different stations of pixels, and then you can form the mean across all the stations, respectively pixels. And what you will find is that the temporal dynamics from all the stations and the pixels tend to be the same, because essentially the soil moisture variability in time is driven by precipitation and evaporation. but they made different absolute values. So even if you then have like in situ measurements at the point scale, you can relate it to a coarser scale. There's a correlation between it. The only thing you typically don't know is if the station tends, for example, to be wetter than the regional mean, or if it tends to be drier than the regional mean, or if it's kind of perfectly fitting within the regional mean. Anyhow, this kind of temporal stability is why, if you look at time series for brightness temperature or radar data or in situ data or for model data, we actually can compare measurements across spatial scales. Otherwise, if this would not be the case, you would have to answer your question yourself, why would you be able to even compare like 1 kilometer Sentinel-1 data with in situ measurements that is only representative of a very small patch of soil? This kind of temporal stability concept is also what's now behind approach that we use for downscaling surface soil moisture data from the advanced spectrometer. So with the advanced spectrometer, we are now moving to kind of a new spatial grid at 6.25 kilometer and a spatial resolution of about 15 kilometer. I'm sorry, I hope you don't hear the noise, but right now we have construction work here going on in the building. I hope it's not too bad. So you see here on the left side is our new spatial resolution ASCAT product. And what we do is we bring it to a finer spatial scale at a 500-meter grid using static parameter derived from Sentinel-1. Essentially, this is trying to use an optimal interpolation of the left product here on the right side. So you see there's much more spatial features on the right side. And it, for example, goes closer to the coastal lines, and it goes closer, it's better in terms of representing inland waters. It's better in dealing with issues like in urban areas. But overall, the spatial resolution or the spatial information content is not so much better on the right side than is to the left side, as it may appear here. So one of the key messages of today's webinar is that if you start using these high resolution products, you need to be very careful what is actually meant by this term resolution. The problem is that there's two terms. The one term is the resolution and the other term is the sampling. Yeah, so the resolution essentially tells you about the information content of the data. So what is kind of the area that my measurement represents? The second term is the sampling. So how often the data are digitally represented. So it's basically in terms of the satellite image, it's the pixel size, and in terms of a model, it's like the model grid. And the point is, these are two different terms. And if we're in an ideal scenario, basically the sampling would be twice the spatial resolution. So if, for example, if you have a spatial resolution of 40 kilometers, the optimum sampling would be in the order of 20 kilometers. So if this 20 kilometer is basically would then correctly display the information content of this data set with its spatial native resolution of 40 kilometers. This is referred to as the Nyquist-Shannon sampling theory. Now the interesting thing is, and really take note of this, that most people always talk about resolution, as I have done now also in the past slides. But in the end, most of the time, actually, we mean sampling, because sampling is always very well defined. People know the spatial grid on which they're working, on which the satellite data are displayed, with the pixel size. But unfortunately, the spatial resolution is often not well known. Coming back to that example that I showed you before. So here in this case, I know exactly that this data is represented on a 500-meter grid So I can precisely say this is a 0.5 kilometer ASCAT data product, but I'm not able to tell you exactly the spatial resolution content of it. Yeah, it certainly will be better than the one of the data shown on the left, but it's also not much better. So maybe we have here data sampled at 6.25 25 kilometer with a spatial resolution of about, say, 15 to 20 kilometer. And on the right side, we have then a product that is being sampled at 500 meter, but say with a spatial resolution somewhere in the order, say, between 10 and 15 kilometer. So the inherent information content here is much coarser as it visually appears. And this applies to many other of the existing soil moisture products. So if you start using a product, do always check how the data is being derived so that you understand what's the real information content in the data. Yeah, so for example, you might be interested in mapping irrigation at a very fine resolution, and you might be using a product where you say, well, I should really see these irrigated fields. But in the end, it's not possible because the data is just sampled at that high resolution, but it's not contained in this data products. So that could be like one of those questions you can ask, do I see the information that I really need? So there's a very clear need that we go to products that stay at, that provide also this information at this very high resolution. So it's not just sampled at high resolution, but also on a fine grid, but it's also representing the real information content. And the real information we have there in the microwave domain is then using synthetic aperture radar data, as they're now coming from Sentinel-1 and very soon from the SAR satellite. So the typical procedure then to go from high resolution SAR data would be that you first aggregate the data to a coarser spatial scale, where you can do a lot of pre-processing from going from the high resolution to a coarser resolution. And once you have this kind of tailored backscatter product, you apply a model and do the retrieval to go to a coarser resolution surface soil moisture product. Along with the SAR data, you can of course also use auxiliary information, like for example, leaf area index data to guide and help the retrieval process. One product that is already available in this way is from the Copernicus Global Land Monitoring Service. It's a surface soil moisture product from Sentinel-1. Unfortunately, at the moment, it's still only available from Europe, but we are working to start already rolling it out to more areas. And the first continent it will be rolled out will certainly be Africa. So we hope, depending on decisions of the European Commission, say that in about 2 or 3 years, such a product would also be available in Africa. So here you see the link to the website of the Copernicus Global Land Monitoring Service, and you could then, for example, display the surface soil moisture products here with this data viewer on the website. And you can overlay a couple of soil moisture data. And here this looks so kind of, you see the stripes from the different orbits so clearly, because these are measurements from different days. And of course, soil moisture varies quite a lot from day to day. So that's why the striping and orbited boundaries can be clearly seen. The method we use here was developed already many years ago based on Envisat ASA data. It's still using a rather simple model, kind of a change detection approach, where we say that the observed backscatter is like a minimum backscatter. This is like a backscatter of a completely dry surface. And for each pixel, there's a certain sensitivity. And that's then the soil moisture content. And this last term here is to account for different incidence angle effects. So what I wanted to show here is, like, if you do this kind of retrievals, you parameterize your model for each individual pixel, and each individual pixel has specific properties. So a specific backscatter for very dry conditions, as particular sensitivity to soil moisture changes, and a different incidence angle behavior. So those maps you see here were produced for Oklahoma in the United States. And you see how, and Oklahoma is like, goes from a wet eastern part to a very dry western part. So here's like still forests, and then it goes over to agricultural land and then into prairie land. So where we have dense forest, the sensitivity to the soil moisture is very low. And the more we go into this agriculture and prairie land, the higher the sensitivity to soil moisture becomes. So also the product quality becomes better here from the east to the west. And using Sentinel-1, Envisat ASA, we also produced the first continental scale soil moisture product about 10 years ago. So this is like a surface soil moisture time series aggregated for different months for different years. And you see an animation of how soil moisture changes over the Australian continent. Well, Australia has a very dry interior region. There still can be like substantial rainfall during parts of the year on particular years, but overall the interior is wet, and it's more like the northern and eastern parts and the southern parts that are wet, but otherwise there's very little soil moisture also there. We later adopted this method that we started developing for Envisat ASA to the Sentinel-1. While Sentinel-1 in principle is extremely well suited for soil moisture retrieval because it gives you a very good spatial temporal coverage, particularly in areas like Europe, it has some challenges in order to actually apply the different algorithms. Like one challenge is that the repeat coverage of Sentinel-1 is extremely well defined, with the effect that you see it here in this pattern over Europe, that some areas are very often revisited, while the next field or the next, say, town may be much less visited. So you see here that these very dark blue areas are areas that are well covered by the different orbits of Sentinel-1, and then the lighter covers, the lighter areas here are much less well covered. So it can happen that, again, just from one field to the next, the number of acquisition drops by half. What also makes this kind of acquisition strategy very challenging for the retrieval is because if you deploy now, if you develop models to work with this kind of data, you must make sure that these models have parameterizations that don't see those striping effects any longer, but they really can account for all these changes. That has been a very important part of our developments for doing the Sentinel soil moisture retrieval. And what you see here is those information we shown at first before for Oklahoma. So here's the dry backscatter reference, and here would be the high sensitivity. So looking again here at the high sensitivity, and if you're familiar with, say, for example, Italy, you would have high sensitivities here in the Po Valley, where there's lots of agriculture. And here in those mountainous regions where you have also dense vegetation, the sensitivity is lower. Also here, that's also visible here in this land cover map. Yeah, and here you would see an animation of the Sentinel-1 surface soil moisture data. So this is an animation we did in 2018. So you can see how from day to day, the coverage changes from Sentinel-1. What you can also see is that if you look at one particular orbit, you also see this kind of striping in three parts. This is because of the peculiar measurement geometry of Sentinel-1, that it does acquisition along these three stripes that are later stitched together. And initially, they were not very well calibrated, so that we saw some striping effects in the data. In the meantime, this phenomena has become much, much better, and those stripes have largely disappeared. But sometimes you still see them there if you have like one image. As you see here, That's clearly one stripe, then a second next stripe, and here next stripe, and in intermediate you see these boundaries, these artificial boundaries. Anyhow, what's nice with the Sentinel-1 data is that this is like a scene from the summer months, from July, where you can have like larger rainfall events, but also like localized thunderstorms. All these events are very nicely captured by the Sentinel-1 data. Of course, with these products, we do regular validation exercises, and the validation is more or less using the same approaches as we have developed for coarser resolution satellite data, like the SMAP, SMOS, and ASCAT. So it's essentially a time series comparison where you calculate standard metrics like correlation coefficient or root mean square error, or more complex measures like triple collocation errors. Here you see two examples of time series from the Sentinel-1. This is in red, and here's an in situ time series from the Remedos network that I already showed you first data, and here's a network from Romania. Yeah, so Sentinel-1 data are much more noisy, of course, than the in situ data. Sometimes you see also like orbit effects if they're not perfectly accounted for in a certain pixel, but overall in these two cases the correlation are very satisfying. Is there a question? Okay, no. Yes, somebody is leaving. Mm-hmm. Yeah, and when you do this kind of assessment of those products, of course you can do it then for many different stations within your area of interest. Like here we have done this for available in situ networks in Europe, and you can see here like blue colors mean that the correlation is with the set with in situ data is pretty good, and white means that there's very poor correlation. And you can see, of course, that there's some stations are much better than other stations. But overall, say we are quite happy with the kind of correlations that are being observed. Also, what you should kind of be prepared to is if you do this kind of validation of this high resolution data is that the metrics can change very strongly from year to year, because at that spatial scale, the retrieval becomes more complex. And if, for example, within an agricultural setting and within your area, they have a very different crop rotation, or they have crop rotation, so that the crop types change a lot from year to year. Also, the quality of the soil moisture retrievals can be impacted, so that you can have a very good year with very good correlation, and the next year the correlation is much poorer. Now, this is, for example, you see here for that particular network here, that this is this Romanian network. So this is the correlation over the years from 2015 to 21. So overall satisfying correlation. But if you look only at the year 2022, we see that some stations are much better, but there are also stations that are highly negatively correlated. So there obviously that is a hint that like changes in land cover and crop types can have a huge impact on the quality of the data. This is, of course, a active field of research of how you can make the products more robust, so that they are not responding so strongly to these kind of changes. But again, coming back to this capability of the Sentinel-1 data to depict rainfall patterns, this is here from a paper from 2018 where we showed like the soil moisture maps from July the 10th to July the 11th. So you see the change in soil moisture from this day to the next day. And if you compared this to rainfall, there was like a rainfall that moved from the north into the Po Valley, and this kind of wetting front is clearly seen in the soil moisture data. Here's another example from the Netherlands, where we just have like one soil moisture estimate that was acquired at around 6 o'clock on the 22nd of July 2016. So it was overall a rather dry day. So most of the measurements are pretty low, except you see here this blue striping here. This is where the soil wetted up to a rainfall event. And this can be nicely reconstructed if you look at rainfall radar. So radar observed rainfall data from ground station radar network. So you see here that animation starts around 3 o'clock in the morning, and you see how the rainfall area builds up and moves northward, and how it leaves like the wet soil at 6 o'clock. What you can see that overall the area matches quite nicely, but there's also differences. And that's also clear because the ground-based radar observing the rainfall clouds sees the water in the clouds. But then water also needs to fall down. And obviously, while falling down, also water can move. So there's a perfect match between of what you see from the precipitation radar to the Sentinel-1 estimates from Sentinel-1. So also here an added information content from the satellite data where actually the rain is falling. So Sentinel-1 data are kind of really useful. Still they have like one important disadvantage is that the temporal coverage is much poorer than you would have with SMOS, SMAP, ASCAT, or EMSA2. Yeah, in Europe, we are in a good situation that we have measurements roughly every 3 days. In Africa, it's much poorer. There, the coverage is more in the order, say, from 6 to 12 days. Now with Sentinel-1B, unfortunately not available any longer and waiting for the launch of Sentinel-1C. Yeah, the coverage is sometimes not really satisfying, and you're not really able to observe fast changing soil moisture processes, unfortunately. So there is good reasons to start merging the Sentinel-1 data, like with other satellites, soil moisture data from ASCAT, SMOS, SMAP, etc. And this is another product we've developed within the Copernicus land monitoring service, where we ingest surface soil moisture data from Sentinel-1 and surface soil moisture data from ASCAT, and we fuse them with a so-called soil water index method, where we also not just fuse them to kind of make a more complete product, but also go from the thin remotely sensed surface layer to the root zone layer with a simple formula. And what you can get then is a product that looks like this here. That's now a product that is available every day, combining the ASCAT information and the Sentinel-1 information. So you have much less missing values than you would have with Sentinel-1. And when you're looking at it, there's also a lot of spatial details in the product. But again, be careful, because we combine ASCAT data and Sentinel-1 data, you cannot expect that it has the same spatial resolution than just using Sentinel-1 alone. So if we combine data that have a resolution of, say, 1 kilometer and data that have a resolution of 25 kilometer, the resulting information content is somewhere in between, say, 10 to 15 kilometer. So the sampling here again is at 1 kilometer, but the spatial resolution information content is at 10 to 15 kilometer from this product here. When you can of course now also compare that product to in situ soil moisture measurements. The immediate benefit from there is already that again we can now produce a soil moisture value every day rather than every few days, and then also in this way the comparison to in situ data and model data becomes also much better than just with Sentinel-1 alone. Okay, see another question. Do you think that soil moisture, surface soil moisture obtained from space is more related to rainfall and not to irrigation? That's a very good question. I'll come back to this later. Of course, the information observed by Sentinel-1, it doesn't care if the water comes from precipitation or irrigation. So that's a very big difference to model estimates of soil moisture that uses input precipitation data, because they cannot predict you the irrigated areas while the satellites see them. And that's I'll come like at the end, it's like one of the applications that we do a mapping of irrigation areas and irrigation amounts using the soil moisture data obtained from Sentinel-1. Yeah, so now I've shown you a couple of operational products that are available for Europe. Now I want to show you a little bit some improvements that we are working on to make the products better. And these improvements will become available in a couple of, say, years. And within research projects, they're also available right now. So we are working both on making the pre-processing much better. So we work here on improved masking of the 20-meter data, that we only consider measurements that are taking over pixels that show a sensitivity to soil moisture, ignoring areas like dense forest, urban areas, water areas, etc. So that we have here an optimized 500-kilometer backscatter pixel. And then we use different approaches to go from the backscatter to the surface soil moisture products. So we use more complex model also in the retrieval. We also go more and more into machine learning to do parameterization of the models. You see here is another question. Is there any difference between using surface soil moisture or soil water index to represent soil moisture? And if there's no difference, which one is preferable? Well, there is sorry, I think it's good if, I hope the others don't mind if I directly react to those questions. Let me illustrate here the difference. So, so the surface soil moisture data just represents the first few centimeters of the soil. These are typically in the order, say, of 2 centimeters, 5 centimeters. The soil water index data, there's different kind of levels contained within there, represents the soil moisture within the soil profile, say down to say 10 centimeter, 20 centimeter, up to about half a meter of the soil. So yes, there are already different physical quantities, and they also have a different temporal and spatial dynamics. I think the soil water index is for many applications the better product, because for many applications you need to have an estimate of the profile soil moisture content. Just for example, thinking about how much, if you have the question how much water is available for plants, it's more like how much is in the profile rather than at the surface. It's also, if you think about runoff, say it's a question of how much water is in the complete profile and not so much how much water is just in a thin surface layer. So I think for most applications, the soil water index is preferable. And it's also easier to use because the soil water index can be produced at predefined times, say at every day at around a certain time, while surface soil moisture is really only valid for the acquisition time of the satellite. Yeah, so it makes a difference if you take surface soil moisture data at 6 o'clock or at 9 o'clock or 12 o'clock for the surface soil moisture product, because the profile soil moisture content is already very much less. You can, for example, take measurements every day at 12 o'clock. Yeah, so in that sense, I think it's much easier to use. Okay. So let's jump here. I see, okay, I see a follow-on question. Okay, no, thanks. So now we are looking into how can we optimize the SAR data to the soil moisture conditions. And one obvious idea is that if you're over dense forest areas, In a dense forest, even C-band data cannot penetrate. Also L-band data cannot penetrate. So with all the microwave frequency, if you have really dense forest, if the tropical forest, or if you have very dense forest in mid-Europe, you only get information from the vegetation canopy, not from the soil moisture. So you then can say, well, why would you use those measurements over the forests? Let's exclude them. And this is what we did here. So before aggregating to the 500-meter scale, we used available information about forest coverage to mask those forest areas before aggregating. And those shows here the correlation with external reference data before and after masking. So after masking, the correlations overall improved throughout the range. For example, see here, here in Eastern Europe, we have here lots of forest, or lots of forests up here. So once you mask those forest areas, the correlation with external reference data improved dramatically in some areas. Another very important effect is that is important, also very, very much in Africa, is the so-called phenomenon of subsurface scattering. Because if the soil is very dry, then we also see scattering elements below the soil surface. Yeah, so imagine you have like a layer of sand on top of rock. And if the sand is very dry, you get a very strong signal from the rock. There's a little bit of damping from the sand layer, but overall the signal would then be dominated here by this rock surface. Now, if this layer of soil gets wet, two things happen. Firstly, the signal from the top increases. This is the normal kind of soil moisture signal we see from other areas. On the other hand, the signal from the rock is strongly dampened. So with the overall effect that if this layer of sand is wetting up, backscatter may first go down, and only when it's wet enough, it goes back up again. So in such environments, as you see here, a picture from Morocco, it may be that the data from the different sensors show very strong anomalies. And with Sentinel-1, we can now map those areas where we get subsurface scattering signals in very much details at 20-meter scale. Here's already a bit aggregated to 1 kilometer scale for Spain. And you see here that in the drier parts of Spain, where you have also this kind of surfaces, that you have these anomalies in there. What we do in order to kind of avoid this phenomena is, again, we mask it. There's always areas within a 1 kilometer pixel where the soil is deep enough so that they don't have this problem of a strong subsurface scatterer. So in the end, again, I just look for those areas where I get a good backscatter signal and only use this then to derive my backscatter at 1 kilometer scale. So what we are now doing is, in the pre-processing, we use the original data. We filter the data for extreme values that cannot represent real soil moisture values, and then we filter out all those areas where, for whatever reason, we cannot be sensitive to soil moisture. So this can be water bodies, this can be urban areas, this can be dense forest, this can be the subsurface scattering areas. And then we get a measurement of backscatter that is optimized for its sensitivity to soil moisture. Of course, after all this masking, there are some areas, even at 1 kilometer scale, where we don't have information, but that, I mean, that's clear. If you have like a very large forest area, we can't get information in there, and you anyhow would have to mask it. Interestingly, there's also like some areas, like urban areas in there, where we don't mask it. This is because in many urban areas, you still find grass areas that give us some sensitivity to soil moisture. So if there's enough open space within an urban area, you still might get an estimate for soil moisture. Yeah, so the next step we then do is we test different retrieval algorithms. The one retrieval algorithms that is operationally used by the Copernicus service, then a more kind of a water cloud approach, a so-called zero-order radiative transfer model, or a more complex first-order radiative transfer model that we refer to as RT1. Yeah, this RT1 model is already quite a complex model in which we try to characterize the vegetation scattering properties through a phase function. So imagine you have like here an incoming radar beam, and here's then the vegetation element. Yeah, we can, for example, say, well, give us so much forward scattering and give us so much side scattering. So this function can be defined. And then there's like the contribution from the soil surface. And also there we can say, well, give us this kind of scattering behavior in the different directions. So it's a very powerful first order radiative transfer model that can simulate contribution from the soil surface, contributions from the vegetation volume, and then interaction terms between the vegetation and the surface. In principle, it's a great model. For the Sentinel-1 data, it's almost an overkill because, as you can imagine, if you want to parameterize this kind of model, you have many different parameters, and Sentinel-1 data in terms of the multidimensionality, they are not that great. So you need to live with a very strongly simplified version of this very powerful model in order to use it. But obviously now we can parameterize this model for different data, both Sentinel-1 and ASCAT. So in the first paper, we did it on the ASCAT, but now we also have like data for Sentinel-1. I see there's another question. How can we use data from SAR to distinguish between surface soil moisture and root zone soil moisture? Well, I don't think that you really can use SAR to distinguish between surface soil moisture and root zone soil moisture. I mean, of course, there's the idea that you use different frequencies, say from C-band, L-band, and sooner or later, we're also going to have P-band data, and they all sense to different depth. So there's a certain possibility to use different frequency to distinguish between different profiles, but you're not coming that far. Maybe we're talking about profile within the first 10 centimeter. There's also the possibility that you use interferometric techniques where you use phase and amplitude information to disentangle different contribution from different depth. Yeah, I mean, there's some very good research work going on, but at the moment, there's no operational products yet that is available. So if you would like to test these kind of things, you're basically, yeah, you have to design the research yourself and for example, do interferometric processing or use data from different satellites. But it's certainly very challenging. It's not a simple one. Now here's results from the application of the RT1 model to retrieve soil moisture of Italy. Again, I see the correlation with an external soil moisture data set. And green colors means the correlation is very good, and red colors mean there's, well, yellowish color means there's no correlation, and reddish colors mean there's a negative correlation. And here in Italy, we see in some areas these reddish colors indicate there's subsurface scattering. So after masking of those subsurface scattering areas, you get positive correlations throughout of Italy and also here Sardinia, also on those parts that are really kind of desert-like environments where subsurface scattering can be strong. Yeah, this kind of data have already been used, and for example, in public media outreach, there has been a very strong drought in Italy last year. So the Po Valley has been extremely dry. The Po River has almost dried out. And say the Sentinel-1 SAR moisture images have been used to communicate these very dry conditions and the drought situation. And a colleague from Italy, Luca Brocca, has twittered those results, and within a day there have been 60,000 views. So one can see how people react to this kind of data if there is a crisis situation. So it can have a very powerful communication effect if you show it to people. Yeah, and here then we kept on working, and what you see here is then after all this pre-processing and applying now RT1 to the complete Mediterranean area, you see here animations. So I think looking at the data and yeah, it's certainly our best surface soil moisture retrievals from Sentinel-1 we have produced so far. Also improving compared to the operational available Copernicus data. So at the moment we are kind of discussing with the European Commission that these kind of improvements in the processing would be brought into the operational case. I hope you see the animations fine. So maybe show one again. So we start here from January 2017. We run through monthly time steps from the year 2017 to the year 2021. Yeah, looking at the Mediterranean, there have been some very dry years like 2018. And we also had some, like in summer in 18, you've seen that there was also been wet. So we really have very extreme years in these periods, from very wet to very dry. Also in Italy, you might have heard the droughts went directly over from an extreme drought condition to flooding. That was just happened a couple of weeks ago, that we really went from like historically low soil moisture conditions shooting up in terms of soil moisture and then causing flooding again in the Po Valley and some other parts of Italy. It was just amazing to see. Yeah, and how can we use this 1 kilometer data? I'm just showing you 2 applications on which our colleagues from Italy are working. The first application is that we exploit the sensitivity to precipitation to estimate how much rain has fallen. This is an approach called SM2Rain, where you invert a land water model, and rather than deriving soil moisture from precipitation, you estimate precipitation by looking at changes in soil moisture at the surface. This is at the heart of this algorithm. Yeah, our colleagues from Italy applied its SM2Rain algorithm to both ASCAT and Sentinel-1. Again, here at the Po Basin, you see here the rainfall maps for the Po Valley. So again, this is like a correlation to independent measurements, where dark red means rather good correlation, and yellowish color in this case means very poor correlation. You see that overall ASCAT gives us rather good but coarser resolution rainfall data. With Sentinel-1, we see much more areas that have very poor correlation. This is kind of the mountain tops where we have rather poor results. But in the valleys, we got very good results. And overall, in those agricultural areas where there's no irrigation, results are pretty good. Results are not, say, this comparison to independent precipitation data starts to be very poor in irrigated areas, as we have here in the Po Valley. There's lots of irrigated rice fields in this area that cause then these very low correlations. But what's certainly very interesting about this SM terrain 1 kilometer products based on Sentinel-1, that's a real 1 kilometer precipitation estimate that you have challenges to get even from ground-based radar observations, and not to speak of ground-based observations. So we think there's a lot of possibility to use this kind of product in combination with the other products to get an improved fused precipitation product. Yeah, and the last slide is coming back to the question from before. Obviously, if we detect soil moisture, we cannot distinguish if it's coming from rainfall or if it's coming from irrigation. So you could now attempt to estimate how much irrigation was there by running a land surface model that is being fed by observed precipitation and matching it with the satellite derived soil moisture estimates. Say, for example, if there was no rainfall and the land surface model tells you, well, this patch of surface should be dry, and the satellite tells you, no, this is actually wet, the inference could be, well, there was irrigation. So this is the basis of this approach. And our colleagues then have used the Sentinel-1 data for mapping irrigation in Spain in the Ebro Basin. And you see here estimates over the complete irrigation season from 2016, 17, 18, and 19. You see spatial patterns, rather similar from year to year, but obviously there's also differences in terms of how much water was brought out from year to year. One challenge with this kind of very new method is that it's difficult to get information about irrigation in the field. So the Ebro Basin is one of those basins where actually there was information that we thought is actually quite good compared to other regions. And when we compare then the in situ observations with the satellite data, this grayish area is the one from observed on the ground. The black line is the one estimated from the satellite. Obviously, there are differences, but overall, we are quite happy that we already achieved this. Yeah, and this is basically just the start and one of the first publications. So I'm sure we will see a very exciting developments in the next few years that will give us then estimates of irrigated areas and how much irrigation was used over the years. Yeah, and one last slide is we have right now a new project where we're working in Mozambique. I'm not sure if a colleague is here from Mozambique, but we are working there also now to derive soil moisture data from ASCAT and Sentinel-1. And we have done our first Sentinel-1 soil moisture retrievals for Mozambique. And overall, this is an area where the retrievals seem to work quite good, judging from the correlation we achieve with independent model estimates from Area 5 land. And you see typical time series here. This line here would be from Area land, and the red line would be the soil moisture from Sentinel-1. Maybe looking here at the Area 5 time series, this is more what you like, what possibly you're familiar with. But basically, it means the model tells you at some point in time, this is already completely dry, and it doesn't get drier. Sometimes with the Sentinel-1 data, we say, well, at the 1 kilometer scale, we don't see it's yet completely dry, but we continue to dry out a little bit more. So now this is up to having field investigations or more investigation to actually know what's the real case. But overall, with models, you also live with certain assumptions. They're bound by a minimum soil moisture content and absolute like a maximum soil moisture content. And many models, once they've dried out, they don't come back that easily any longer. Yeah, so that's up to research to determine the added value that we achieve here from Sentinel-1. Yeah, there's a big outlook to one of the first global available products that will come from next year on, based on the NISA satellite. It's already introduced it in one of the first slides. That's a very fantastic instrument built by NASA together with the Indian colleagues. You see here this amazing antenna, 12-meter radar reflector antenna. The radar has an L band and an S band. And what the NASA team will try to do is they will produce 4 global soil moisture data products on a 200-meter grid. So it's very ambitious. Yeah, and data, if the launch will happen in January of next year, that's the current planning, then you might have the first 200-meter NISA-based products by the end of next year. We're also very curious to look how the products look like. So that brings me to the conclusions. So I've shown you now a couple of different products that come with a sampling of 1 kilometer or better. And just again to highlight, if you use those products, always check how they are derived and try to distinguish between the sampling and the real resolution, because that has an impact on how it will behave in the application and if you get the information that you're looking for. So at present, most of these high-resolution products are still available only at continental scales, but the number of global products are growing. So obviously, you can start with some research and then prepare until they become operational available. But what's certainly still the case is those products have not yet reached the same level as maturity as SMAP, SMOS, ASCAT products, but still have many more difficulties to face with. And one of those difficulties is that the validation of those products is still, say, at the beginning. And while we may check the temporal dynamics of those products reasonably well, using methods that we know from ASCAT, SMOS, and SMAP, the spatial details are still very difficult to validate. And obviously, because we have much less understanding of those products yet, they're also more difficult to apply. So doing applications will also be more challenging than with the coarser resolution products. So I hope that you found my talk interesting. Would be very happy to take questions from you, from those that have already posed some questions. Thank you very much for this. So thank you. And other questions? Yeah, there's one question. For the period between 2000 and 2010, is the way to have like 1 kilometer soil moisture information over Africa? Yes, you could use data from the Invisat ASA that provided data within that time frame. Invisat ASA had a mode that was called global monitoring mode that gave rather frequent observations of Africa. The radiometric quality of the data wasn't the best, but we've done retrievals of soil moisture within a previous project at that time, and the data looked interesting. So there's a way to get to 1 kilometer data, albeit with a higher kind of uncertainty than you would have from current products. There's a question just to make sure. Do you prefer the use of coarser spatial resolution products? No, I mean, we are working to get to higher resolution. What I'm trying to bring the message is that depending on if you're a researcher or if you're more on an applied side, an operational side, the answer is different. Say, if you're somebody expecting readily available data for your applications, you're still safer to work with coarser resolution data than finer resolution data. Yeah, so they're more readily available, they're more mature, you can expect to work with them for much longer. Also, I think in many applications, people overestimate the importance of the spatial resolution. Yeah, many things like drought monitoring. If you then like have data on, say, a 6-kilometer grid, it's, you know, often we sometimes had the experience that people complained about the poor resolution, and when we then gave higher resolution products to them, they said, well, don't give us so much data, we don't know what to do with it. So if you're more on the application side, I would first start with coarser resolution data to check how far you can come. And if you then still say, no, I need higher resolution because I need to see those details, then you can go to the emerging finer resolution products. Are there more questions? Thank you very much again for this question. Allowed to talk, okay. So I allowed somebody to talk.
Sure, Professor. Thank you so much for the nice presentation.
Thank you very much.
Yes, I was not able to send it. I don't know. The chat was not. It says like disabled, so that's why I requested my. Yeah.
Sure.
So I have. I need some help. Especially, I was working in experimental basis, especially in. There were 2 field experiment. I was planting some trees, seedlings in 20 by 25 meter plot, and the plants were 1 meter apart from each other in the field.
Mm-hmm.
I want to, I was also supplying with irrigation, additional water, just by trying to analyze the field capacity level and other things using the core sampler method only. So I want to confirm now with using the any high resolution remote sensing methods. Which one would you think is applicable for this? Is it possible also to get 1 meter resolution based on each plant? Can I check these things using RS?
I think for your application, those SAR-based products are also not enough. I think in your case, it's better if you use very high resolution optical data so that you check soil moisture indirectly by looking at changes in vegetation and temperature, so that you use more indirectly, again, vegetation and temperature gradients, for example, as an indicator on the positive impact that your replanting has. Yeah, so I wouldn't expect that you see any information from our data from these SAR-based estimates.
Okay, thank you. Thanks, Professor.
So sorry not to be bombastic, but it is very high resolution. I think one can learn a lot from higher resolution optical and thermal data. But you basically you need to, based on your expert knowledge of field conditions, you can make indirect conclusions if it was successful or not. Good. Any more questions? No, doesn't seem to be the case. So thank you very much for your attendance and the very good questions. And I wish you a very good afternoon. Thank you very much. Goodbye.